Today we're going to apply our understanding of transformations to sine and cosine functions. I have shown below here a sine graph, a basic sine graph, which has an amplitude of 1 and a period of 2 pi. Now remember that amplitude is calculated by taking the highest y value minus the lowest y value and dividing by 2, which is where we get our 1. Our period, remember again, is the horizontal distance that it takes for the graph to go through one complete cycle. So your standard period for sine or cos is 2 pi. Your standard amplitude is 1. Now let's start making some transformations to the graph by introducing 4 parameters in different positions. And let's begin with a. We're multiplying a by the function sine x. And you should remember that you should be able to anticipate what's going to happen here based on your study of transformations in the past. In fact, it's a vertical stretch of the graph. So when a is 0.5, the graph has been vertically stretched by a factor of 0.5. And you'll notice that what that's changing is the amplitude. Our amplitude is now, if we apply our formula, the highest y value 0.5, subtract the lowest y value negative 0.5, which is a distance of 1, divide that distance by 2, and your amplitude is now a half. So you might conclude that the amplitude is actually the a value. Okay, but consider that if we made a negative, that reflects the graph across the x-axis. And because our calculation for amplitude is still highest y minus lowest y divided by 2, our amplitude is actually 0.5. So it's the positive of the a value. One more thing, you might also wonder if shifting the graph up and down is going to affect the amplitude. Well, the sliding of the graph up and down is, as we know from our study of transformations, caused by the constant at the end. So if I were to make that constant at the end 3, it should shift my entire graph up 3 units. And you'll notice that my amplitude would be calculated by taking the highest y value, 3.5, minus the lowest y value, 2.5. 3.5 minus 2.5 is 1, dividing by 2 to get a half. And so you'll notice that the amplitude is related to the a still, despite a vertical shift up and down, except it's the positive of that because amplitude is always positive. The d, not surprising, is a translation up and down. And let's just let this roll for a minute. Depending on what d is, it slides the graph vertically. And we call that vertical displacement. If d is 2, then my graph has been translated 2 units vertically. Let me just put my amplitude back to the standard amplitude. A d value of 2 is a vertical displacement of the graph 2. It slides the graph up 2. d negative 2 slides the graph down 2 units. So let's just summarize a couple of these results based on making vertical changes to the graph. The amplitude was affected by the vertical stretch, which is affected by the value of a, and since amplitude is always positive, amplitude can be found by taking the positive value of a. If a is negative, we know that the graph reflects in the x-axis. And the other vertical change we talked about was d, which is the vertical displacement up and down. If d is positive, we're moving up. If d is negative, we're moving down. Now when you're dealing with sine and cosine functions, it's the horizontal transformations that are a little harder to follow and to graph on paper for sure. So let's start with b, which is b times x. And when we multiply x by a constant, we anticipate a horizontal stretch of the graph. So if I were to make my b value 2, replacing x with 2x should cause a horizontal stretch of the graph by a factor of a half. So all of the x values on the current graph should be halved, pulling all the points closer to the y-axis. And you'll notice that the effect of that was that the graph goes through its cycle in half the time it did before. So the period is no longer 2 pi, it's half of that, pi. If I were to make my b value 0.5, then I should anticipate my original points being multiplied by a factor of 2, causing the graph to take twice as long to complete one cycle. So no longer a standard period of 2 pi, but double 2 pi to 4 pi. So we can see that the b is affecting the period. Specifically, the reciprocal of the b value multiplied by your standard period of 2 pi is giving you your new period. The other thing to keep in mind is that we can make b values negative, and when we replace x with negative x, we know that causes a reflection of the original graph across the y-axis. Put b back to -1. You can see how the two graphs are related. So b, as we've seen, affects the period. Our standard period of 2 pi is changed by a factor of 1 over b. And since b can be negative but period is always positive, we put absolute values around that as well. And so our new period, as a result of our transformation, is 2 pi divided by b. And if b is negative, we know that the graph reflects across the y-axis. Alright, so there's one more parameter we haven't talked about, and that's c. Replacing x with x minus c, we know shifts the graph horizontally. So resetting my parameters, if I were to put c value here of pi over 2, x minus pi over 2 should shift the entire graph pi over 2 units to the right. And indeed it does. Negative pi over 2, pi over 2 units to the left. And so changing c shifts the graph, translates the graph left and right from its original point. And when we're dealing with sine and cosine graphs, we call the horizontal translation a phase shift. If c is greater than 0, remember the minus is in the middle, that's a translation to the right. And if c is negative, that's a translation to the left.